So today we're here with three of the authors of this paper with, I have to say, a lot of authors. It seems like a giant work just from what I could gather from the paper itself and the data collection and the evaluation and so on. So this was a huge thing, but the results are pretty cool. So here with me today are Fei Xia, Brian Ichter, and Karol Hausman, who are three of the authors of this work. Welcome to the channel, everyone.
Thanks.
Thank you for having us.
It's great to have you here. I love the title because it's a bit of a mantra on the do as I say, not as I do, which is kind of the other way around right here. And this idea of connecting robots and language, it seems pretty natural, I have to say. I've seen a number of paper attempt to do something like this, like can we maybe translate what the language model says into the space of what the robot understands and things like this. But this here, it seems like a bit of a new approach. Why did you attempt to do this? Like, why does this seem promising? And why did no one else do this thing yet?
Yeah, I mean, I think to start prior work on using a language model to kind of translate it down. I think we first started out with sort of like playing around with that and realized, I guess, how much information is imbued in these language models and how well they're able to reason over sequences and remember what they've done. But when we really started thinking about applying it to the world, it was sort of odd that there's no way to basically make sure that whatever it's saying actually makes sense for the environment that it was in. And so I think after playing around with that for a while, we were sort of stuck there, okay, we have these interesting plans, but they don't actually make sense for everything that the robot can do. And so we started kind of shifting towards that problem.
Yeah, I think also separately we've been trying to get robots to do many things and learn multiple skills. And this is a very difficult problem. And we were debating kind of the best way to do this, whether we should predefine the skills up front or whether we should just demonstrate kind of anything that comes to mind and label it afterwards. And just connecting these two dots, the language models with the skills that we already have on the robots, seems like a nice way of factorizing this problem. So you have this robot in this environment, and if I understood correctly, maybe here is a good demonstration of that. So you have the robot in these two environments, and these are the environments that exist. Do I understand this correctly? So it's only these two environments. There's no generalization across environments. Yeah, so we've been collecting data in a few different environments. These are the two environments that we used for evaluation. We also have a separate environment that is right next to the environment that is marked as B here, where robots are practicing. But it looks fairly similar to at least the stations that the robots practice on are fairly similar to the stations that you see here. The backgrounds are changing, the objects are changing that we practice with and things like that. We also use simulation as an additional environment that we then try to make look similar to the real world. But we don't really focus in this paper on generalization to completely new environment. We rather try to focus on kind of having a robot do as many things as it could in a single environment.
When we talk about robot practicing things, I guess that's where your method starts, with robots practicing things. And by things, I guess we mean a bunch of very low level, let's call them unitary skills. Like here, for example, find a Coke can, pick up the Coke can, bring it to you, something like this. So these could be things that conceivably we could learn with something like behavior cloning or something like this. How did you decide on what actions are possible for these robots to do on their own, like as a unit?
Some of it is based on what the robot's capable of. Some of it's what gives us a easy reward function. And some of it was sort of motivated by what composes well into long horizon behaviors that you really want to do in the world. Like if we have a robot operating in a kitchen, what would I ask it to do? What's required of it to do that? And how would I break down the task? I think is part of the motivation, really how this robot's going to operate in the world.
Yeah, and also it's interesting to see how this picture changes. So initially we kind of have to come up with these, and we kind of have to think up front, what would a person ask a robot to do?
But now that we have something running, we can actually ask people and see how they interact with the robot and decide on which skills we should be learning next based on that.
Sorry, I want to add that at the beginning we choose pick and place because these are two fundamental skills that can unlock a large number of instructions that we are able to solve. But it is also very easy to add new skills into the picture. Like we only need to have a language description for the skill, and we also need a policy and a value function. So these are all the three things you need to import a new skill into the SayCan framework.
What I like here is that you said you need a policy and a value function. That policy doesn't even have to be like neural network based policy. Conceivably, one skill can be a very classic control problem. I believe when you pick up things, is that correct, that you classically control where the actuator should go? And when you move the robot, you kind of plan in space. So not everything is like reinforcement learned or behavior cloned.
Yeah, so different skills are learned differently. In this case, pick was learned through behavioral cloning on real data. But yeah, for instance, moving around, this is not trained with reinforcement learning or behavioral cloning. So yeah, you can have different algorithms train different skills.
And these skills, just to round out the picture right here, the input is whatever the camera sees, plus, kind of all the states of the actuators. So that conceivably there's an apple in front of you and the task is pick up an apple, and that would be kind of the state from where you operate.
That's right. Yeah, we are going.
And the value function describes kind of how likely you are to fulfill that task.
That's right. Yeah, so the input to the policy is the image that the robot sees that you get at after every action. We actuate the arm by doing end effector position control. Yeah, these are the inputs and outputs.
and also there's a terminate action, right?
Sorry?
So the robot can say itself when it's done.
Yes, so one of the actions that the robot can command is terminate, which basically means I'm done. Now we can move on to the next one.
And okay, so now I guess this is one part of the puzzle. You have robots, you have all these policies for all the little things that the robots could do. These little things were developed by you, by the community. Conceivably, you could also use the large language models itself to suggest new things to train, right, on the basic level. You could ask GPT-3, what would you do right here? And then the little steps you could conceivably train into little actions. But you have this library of things, and now the question is how do you compose them? And that's where the large language models comes in. Do you want to comment maybe a little bit on how does that look in a basic way? How do we combine the knowledge of language models with these skills that the robots can do?
Yeah, I guess at a high level, so the language model already has so much knowledge about the world and how to do things in order and memory and things like that. And the way to get it to really speak in the way that is amenable to the robot, first we show it a few prompt examples. So we show it solving, about 10 problems and breaking it down from the query into the sequence of steps that it would take to solve that. It turns out you can actually not use that and you still actually get some level of performance, maybe half the performance. So the language model just comes out of the box with pretty good understanding of these tasks. We then show it these examples. This kind of brings it into the right frame of thought. But if you do that and you ask for something new, it doesn't fully constrain it in a way that the robot will be able to understand it. So our tasks, along with the image and the states that we mentioned before, also takes in a task ID. So it says pick up the apple. So really what we need it to do is output pick up the apple. It can't say pick up the fruit because the low-level policies are not generalizing to that. So to make sure that every time we actually output things you can do, we, instead of taking the generative output of a language model, we use what's called a scoring model. So when a language model outputs some text, it also comes with a probability that it would output that text. And so instead, we can just like force it to only respond in these ways and say basically how likely it is to respond in that way. So in this case, we get like a score of if I were going to pick up the apple or put the apple somewhere, these are the things I'd likely to respond. These are the things there's no way I would respond. And this gives us some like probability that the language model thinks this is really useful to the downstream task. On the other side, we have these value functions and policies that we've talked about. They're actually, the value functions outputting how likely it is to achieve a task. I think actually there's another slide, one more down. But this is basically, is saying basically these are possible from this state. And so on one hand, we have a language model saying this seems really useful for the task. And on the other hand, we have the value function saying this seems possible. And together they give some probability that this is what you want to do to basically accomplish the high level instruction.
I have a number of, okay, let's just start at the beginning, at the language model level. I see the high level picture. You ask both the language model and the value functions what they think should happen next, and the combination of the two is what then you really do, which makes a lot of sense. When you do ask these language models what to do, right here, you said you essentially you ask the language model for the likelihood of an output instead of letting it generate the output. Was this your first try? Because one could also imagine saying something like, of the following options, which one would you pick, right? And then you list all the options, which would conceivably be more general because you could add options over time and stuff like, I guess you could do that here as well. But was this your first attempt, or did you have some prompt engineering attempts before that?
Yeah, I think at first we tried just like prompt engineering to see like basically what the generative model would output. I think like our initial thinking was we just want the generative model to basically plan as much as we can. But that runs into two problems. One is that it doesn't constrain the output fully. So if I give it all these examples and then I said, how would you put a fruit on the table instead of an apple on the table? The generative model will actually respond with like, number one, find a fruit. Number two, pick up the fruit. And then you need to figure out how to like take that and project it into the final thing that the robot can actually handle. You can project this in some sort of like embedding space, and that works sort of well, but you actually lose some context on the overall query. So I guess the way that we do it is a little bit more like well-founded, so to speak. But the other really nice benefit of this is it gives us scores for everything, which is really interpretable. It lets us like see the trade-off between these two options. So in your example, you said, what if I just said, here are your options, pick one, and the language model would probably pick one. But now you only know that this is its favorite option. You don't know the probability that it would have done. Maybe it's actually okay with the next three options. So this gives us this like interpretable score that we can then combine with the value functions.
Yeah. I mean, there are some caveats to this, I feel, in that, for example, we know that by definition, longer outputs are less likely, right? So I guess it's not too much of a problem for you because most of yours are like 3 or 4 words, but have you noticed any of kind of these effects of just how these probabilities are constructed as kind of multiplications of softmax outputs? Like that's got to bring its own bias into the picture. Have you observed any of that? Have you had problems with any of that, or was it generally okay?
Yeah, it's definitely a little bit of an issue. I mean, I think in general it's also very particular to these, like if you were to misspell a word in there or like have an a versus an an, it's not particularly robust to those in the options. It is in the query, like to what the user might say, but not when you're scoring these options, because if one word is off, then this like multiplication of each word just kind of tanks the entire score. So we did have to be somewhat careful with what we have. One way to kind of like get around this a little bit is if you have some like end of statement token, and if it adds extra words on the end, then it's saying if there's like more to come, that end of token will basically like kind of normalize the rest of it. Like you can't end a statement early. But yeah, I think the other thing that we did try to do is like potentially normalize them. So knowing that this query is longer, perhaps we need to upweight it or have some normalization on the language output. But we found that it wasn't particularly consistent, and there wasn't like just a constant effect across one or the other, and it depends on the way you like referred to the query. And so at the end of the day, we just took the outputs as they were. So it was an issue, but it wasn't like a huge one.
I imagine that there's another factor here. For example, if you say, you said before, pick up a fruit, or please bring me a fruit or something like this, you're essentially relying on the ability of the large language model to sort of recognize that apple is a fruit and kind of interpret that in the same way and so on. So the kind of as the language model estimates how close the things are, did you find this generally an agreement in how humans find how close the things are? And maybe... Yeah, I'm just wondering about this notion of how close things in language are together. Also, what happens if you, for example, have an apple and an orange in your scene? These two things would be quite close together. So even if you said, please pick up an apple, the pick up an orange thing would conceivably score quite high in the language model, which might perturb your things. So I can sort of make out that you have an ideal environment right here, in that you probably picked objects that are distinct from each other, locations that are fairly distinct from each other, right? Such that there's a nice semantic gap between the things. Do you think this is well applicable to a real world setting, or what kind of hurdles could there be with connecting language models and a set of actions in this way?
So I guess the first question was about, do these families kind of align with what you would expect? And that was one of the first things that I was looking at, was like, how well do these scores sort of match up to what you think it's going to be? So yeah, it turns out that like apple and orange and banana are all going to score quite highly when you're asking for a fruit. If you ask for a snack, all the food options are going to score highly. Similarly, drink, soda, any category like that. And it performs about, as you would expect as a human, which is good. But then, it comes to this problem of, what if there's an apple and an orange? Or what if there is an orange but not an apple? And that's where these value functions come in. This is actually like one of the key reasons why we have to do this embodiment grounding. Because if you just asked a regular language model that doesn't know what's there, then how does it make that decision? Maybe it chooses the wrong one. Then your plan isn't really correct, and our policies may not actually work. But the value function tells you, if there is an apple in the scene and no orange, then you're going to see a high value function on the apple, because the pick apple command could work, versus the orange command is going to be quite low. And so that actually lets you sort of like disambiguate this. So in figure B, if it had pick up the Red Bull, if you said bring me a drink and there's a Red Bull but no water, it's going to pick up the Red Bull because that's actually what's there.
And if not, then the instruction itself is ambiguous, right? If you say pick up a drink and there's two drinks, and both are affordable according to the value function,
Yeah, then we think like either is completely fine.
I think it's also interesting because then the robot is making the trade-off itself, dependent maybe on the value function. So for instance, if you ask for a fruit and there's an orange and an apple, but it's much better at picking up apples, maybe it will pick up the apple because the value function will just tip the scale. So it will make some errors in that sense, but since this is interpretable and you can kind of look back and see why it decided for that, it can also inform us as to what skill we should train a little bit more, or which value functions are a little underfitted, and things like that. So it will make some sort of mistake, but maybe that's okay. Like maybe that's acceptable.
I think one like really nice feature of that too is it's not necessarily always like it's better at picking up oranges or apples, but you can see like these objects are in different locations. One may be better for the policy than the other. So we're going to end up doing the one that's a little more robust and a little more likely to succeed, as long as it still fulfills the high-level query.
Mm. Yeah, I like the fact that you have success probability as sort of the ultimate score, because I also thought one failure mode here is that some tasks are inherently harder than others, right? And so naturally your value function would be lower, and therefore you can misinterpret just by the fact like, like this is me, the procrastinator. Like, this thing seems really hard. I'm gonna do this other thing that it doesn't really help, but it's really easy, right? So it's almost too human how the robot would act in this way. So yeah, you have these. What I like here as well is that you have the bank of value functions on one hand, the language model on the other hand, and they are never, if I understand correctly, trained together, right? They're never. In fact, the language model is probably just frozen. So they're never trained together, which means that you could conceivably just add a skill to the robot, train its value function for it, and just plug it in and go.
Yeah, I think we can scale this fairly easily. So we can continue adding skills. We can also change the underlying algorithm on how we train the skills, or how we train the particular skill that we want to add. If suddenly there is a really good script that allows to, I don't know, swipe the floor or something like that, we can also add that as long as we have a value function for it. And also at the same time, if the language model becomes better, we can also swap out the language model and get improvements through that.
I want to add that currently value function is one way that we instantiate affordance, but there are many other ways that we can instantiate affordance. Like, for example, we can directly do prediction. We can also use classical motion planning, like to calculate, for example, length of the trajectory is also, or the probability of success if you do like sampling-based motion planning. So there are many ways that we can come to the affordance, and the method is really flexible to plug in any type of affordance.
I guess a big topic in maybe it's more the space of blockchains and things like this is agents that do an action for you, but also optimize, for example, for cost or for resources or something like this. This could directly flow into that, where you can tell the robot, do whatever fulfills my task, but also costs very little. And this could, if this directly flows into affordance, there might be a normalization issue. But if this directly flows in, you could tune the knobs on these functions fairly easily. So this is the full algorithm. I guess we haven't talked yet about how you extend this to multiple steps, but it is, as far as I can tell, fairly easy in that you do this in sort of a stepwise fashion. So first you ask your language model, your value functions at the current state and the current camera position where what should be done. Then you try to, whatever should be done according to both scores combined, you execute that. And after you execute it, you ask the same thing again, but now the prompt changes, and it's simply that so here, the prompt is essentially I would first, and then first action is decided. And once you go on, the prompt now says I would first, and then whatever was decided on, and then second, and then it's simply the same thing with the next action. Did I get this approximately correct? Do you pay any attention to whether or not the task was fulfilled successfully?
So right now we don't. We assume it will successfully execute. I think some things could happen, like if it fails at a navigation task, say it was trying to navigate to an apple and and it doesn't get there, then the value functions at that next state are going to be quite low. So you're not going to be able to basically pick something up or whatever. So maybe then you end up selecting navigate to the apple again or navigate to a table instead. But we don't have any like explicit success detection. I think this is like one area that we're like pretty interested in going, basically like finishing the job, closing the loop entirely on when you try to do something, did you succeed, telling the language model, and then having the language model adapt accordingly.
I want to show one video from your website, which in this case, if I got this right, it confused me, I guess, a little bit, because this thing right here, if you see, it kind of looks around, sees all the things, right? It like looks and sees, and then it kind of scores the actions and like this. So pick apple, I can't do that. Pick sponge, okay. Bring you a sponge. No, not go to trash can. Place the sponge. Place the sponge is good. And that's the place the sponge kind of outweighs the bring you a sponge. Or like what's going on right here? Because in my estimation, the robot shouldn't even look around initially. The robot should just have its camera position fixed, and then in first instance it should probably figure out like find a sponge or something like this, and then it would move, and then it would consider these next actions. Like what is this video supposed to show?
Yeah, I think your understanding is completely correct. So this is more like a conceptual video where we wanted to kind of get across that it can accomplish longer tasks. But you're right that the way it would happen is that it would look at the current image, then it would decide that it first needs to find a sponge or maybe pick up the sponge if the sponge is already available, then append that to the prompt and continue. So we just wanted to make it short so that you can still get that idea across, but only by having a single image. So it might be a little bit confusing. It doesn't, I think, depict fully how the method works.
Yeah, I think we just got excited by the visual of a language model sort of seeing nothing and then waking up and saying, oh, I'm a robot. Okay, here's my history of what I've done before. Okay, depending on that, what I thought made a lot of sense doesn't make any sense anymore. So it's more like excitement than anything else.
It does look pretty sweet. Like it looks pretty cool, especially like the effects on like the zoom, seeing what's around. You use, by the way, we've not shown this yet. You use these everyday robots constructions, which look semi creepy, but also quite cool. Especially when they pick up stuff, they like hold it behind their back. Like it's like a mixture of a butler and someone who just has a knife and wants to stab you. But pretty sweet, and it works surprisingly well. So maybe we can talk about the results of a little bit next, because my next question would sort of be, okay, how well does it actually work in the environments where you test it on? Do you maybe want to comment a little bit on what were the general results, and then you have some ablations?
Yeah, Fei, do you want to take this, or do you?
Yeah, I think I can take this. So we test this on two environments. One is the real office kitchen, and another one is a kind of a mock office kitchen, showing in figure 5, I think. And we tested on 101 instructions from like 6 categories. So here are the test environment. The A is a real kitchen and B is a mock kitchen. There are 15 objects that we focus on, and also 5 semantic locations. Like these locations are semantically meaningful, like table, trash can, close counter, far counter, and a robot operator location where we define like bring back to you. That's where it is supposed to bring it back to. We test on 101 instructions from 6 or 7 categories. If you scroll down a little bit, it's mainly to test different capabilities of the robot. For example, can it understand synonyms like noun synonyms or verb synonyms? Like what does throw away mean? Throw away means bring something to the trash can. Like recycle means bring something to the trash can. And also structure language, which is just like verb noun compositions. And also we test embodiment, which means we test if the robot understands what its current embodiment is. For example, if I already pick up something, I shouldn't try to find it again because I already have it. Also, we test on crowdsourced. Basically, it's unstructured human queries from like coworkers, for example, and long horizon tasks, which are some of the really challenging instructions, such as I spilled my Coke on the table, how would you throw it away and then bring me something to clean? So that's a really challenging task. The robot needs to understand what does spill mean, like what tools you can use to clean up a spill. So these are the instructions that we tested. And overall, I think we achieved 71% planning success rate and 66% execution success rate. And the hardest question is still the longer horizon tasks. So I think we only have about like 30 or 40% success rate. We are working on improving those like harder success rate on those harder questions. Brian, if you have anything to add?
Yeah, the only thing I was going to say is that the long horizon ones are particularly challenging, both from like reasoning and language side, but a lot of the issue comes with if you have like a 90% success rate manipulation policy, which is still quite high. Every time you do this, you reduce the probability that your overall plan is going to succeed. And so that starts to like both it's a big challenge and we want to get our manipulation policies better and better and each of our low level skills better and better, but also having some sort of like closed loop that so the language model knows to retry would be really helpful here.
And you I saw in the results that it's pretty interesting in that you did ablate a lot of these things. For example, you did ablate if we don't have the language model, and these are the overall success rate. You ablate what if we don't have the language model, and what if we don't have the scoring model, and generally they were worse, much worse in both cases, which was pretty cool to see. And not always the same, except in this one, it is one thing, to understand this correctly, if you drop the generative model, generative uses a large language model, projects to the nearest skill via an embedding, that is actually better than your original policy. Is that just noise, or is there something behind it if you use this verbs category?
My guess is I think it's more noise than anything else. But there were definitely times where, we see it like really fail in certain circumstances. So embodiment, because there's no value function there to tell it that it can't do something, there's a real issue for it. And so there were a lot of failures for anything that didn't have a value function there. I do think we saw some pretty interesting differences between the no value function, so this is the scoring model only without a value function, and the generative model. And so some of the issues with the generative model came around with like nouns, for instance. And this is because when you do this projection, say I said I just worked out, I want a snack. It then projects to, or then the plan will say, bring me a snack. But really what I want is a snack to help me recover from my workout. And so that like little bit of information is enough to say it's probably not like potato chips, but maybe something like healthier. Similarly, like a drink there would lose a lot of its information. And so on the noun ones, we saw that it ended up like losing this information, and that cost a lot of the success rate. Whereas the scoring model did okay across the board, but maybe not as like smoothly in the verb category.
Another really fascinating thing here is, at least in my opinion, just the scale of data collection in this project. I have made a few notes, and at one point it says something like you use a lot of human labelers for example, the success rate of these little policies. So even when you train these little or small unit, let's call them unit policies, you use humans to see whether they're correct or not, and you use 3 human raters per execution, and you give one single sparse reward if 2 out of 3 agree. So like this scale seems immense, right? Is really like, how did you determine this was the best way to spend the human time, and not maybe to gather more noisy but 3 times more labels or something like this? Like, how did this come to be?
Yeah, this is a good question. And I think we are still figuring this out, a lot of these questions, and how to spend human time in the most efficient way that helps the policies the most. And I think there's a question of crowd labeling, as you mentioned. So how much noise can you tolerate in the reward function compared to like the throughput of that? Also, how much time you should spend collecting human demonstrations versus how much time humans maybe should be just supervising robots collecting data autonomously. How much should we be spending time developing assets and policies in simulation and transferring them to the real world? So we are still kind of trying to find the trade-offs between all of these. I don't think we have any very good answers right now. As for labeling itself, we noticed in previous projects that the noise on the reward signal can be really can have a big influence on performance. So that's why we decided to have 3 labelers to agree on the 2 of which we have to agree to market a reward. And we also had additional questions such as, was the behavior undesirable or unsafe? And these are sometimes quite ambiguous. So it helps quite a lot to have multiple people look at the video and tell us what they think.
Did you always have these additional things in? So you have, as you say, and I also wrote this down somewhere, unsafe, undesirable, or infeasible. Did you always have this in, or was this kind of a development that happened over time that you realized, oh crap, we're asking people how likely is the robot to pick up an apple, but there's no apple in sight and things like this?
Yeah, so some of them we added. So initially we knew that safety is a big problem, so we started with that question. Then we noticed that sometimes the robot would do something that isn't necessarily unsafe, but we still don't want it to do it. For instance, it will touch the object that it wasn't supposed to touch, or it will just poke something and it will fall off the table. So then we added the undesirable, which is has a slightly different definition. And we can also optimize for it differently in the reward function. And then regarding the last one, the infeasibility, this is something that we noticed with reinforcement learning algorithms, that if you add a lot of data where the task wasn't feasible, even though the data is technically correct, right? The robot didn't accomplish the task, it got reward 0, but it seems to be influencing the RL algorithms in a bad way. So we added this in addition to prevent that and potentially filter for this data or see how we can change the RL algorithms to handle that kind of data better.
And why do you only give a single reward? I mean, presumably a human watching a video like this could be, every couple of frames could be like, yeah, good job, robot. Yeah, that's the right way. Yeah, oh no, don't do that. Like essentially like Peter Pan or warmer, 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 colder, colder, which would give sort of a much more dense label space. Is this like a technical limitation, or did you also consciously choose to say, no, it's one single reward, and it's 1 when you fulfill the task and 0 everywhere else?
Yeah, so there's, I think, a few reasons for this. First, I think the ambiguity that comes with it. It's already sometimes difficult to decide whether the task was accomplished correctly or whether it was undesirable or not. If in addition to this, you have to add this continuous signal whether the robot is going in the right direction, I think it can be fairly ambiguous depending on what the robot is doing. Secondly, we made a decision some time ago that optimizing for sparse reward tasks would be just more scalable for the future. There are some tasks where it's quite difficult to say whether the robot is actually going in the right direction, and sometimes it accomplishes a task in a surprising way, and we don't necessarily want to kind of eliminate that and introduce human bias of like, well, I think it should go that way. So our RL algorithms that we've been developing have also been optimized for the sparse reward setting. So that was kind of another factor that we thought about when considering the reward function.
So speaking about doing it like humans, there's yet another set of data collection in this project, and that is that not only do you collect the labels, but you also do quite a considerable amount of behavior cloning from essentially learning from demonstrations from humans with another set of data gathered from, you call it teleoperator sessions. How can we imagine such a teleoperator session? Like, how many of these kitchens and robots do you have, and how long does this take to gather a data set that you could conceivably do behavior cloning from?
Yeah, so I think we specified in the paper that we gathered at that point around 70,000 demonstrations for all these different tasks. This is across 11 robots, I believe. we built little stations where the robots, like the stations that you can see in the picture here, where the robots can practice these things and people can demonstrate how to do things. I think we are still kind of trying to see how much of this, if we filter the data set, for instance, how much can we filter it and still get really high result? So I think we don't have very good answers to that yet. But this is something we're looking into, kind of the trade-offs between how many demonstrations you're collecting, how much autonomous data, and so on.
Where is this? Just because this is at Google, which is a company, and sure, there's like a cash cow that generates infinite money, but there's got to be some kind of constraint on you. Or how does this work? Maybe what robotics at Google? What is your mission there, and how do you pitch such a thing to management? Like, essentially we want to collect 70,000 sessions of teleoperated things every time a human, presumably not a random human, because they would just crash the robot out of spite, but like a trained, trusted human needs to sit down and spend their time, and these robots are quite slow as of now. Like, there's got to be a considerable budget behind all of this data collection and labeling and so on. How do you have to make a case for that, or are you relatively free in doing this? Like, how does your work in the let's say in the business perspective look like?
I think in any company you kind of have to make a case, or even in academia you have to make a case for your project, why you think this is how the money should be spent and where the resources should go. So usually the way we kind of justify it is by showing kind of step-by-step results and showing, if we extrapolate this, where this is going to go. So we've done some projects previously where we showed reinforcement learning at scale with 6 robots, or behavior cloning at scale with just 2 or 3 robots. And then we start seeing that with the amount of data that we collected there, we already can see some interesting results. And now if we want to get these robots to do many more things, we need more robots, we need more data. And this is kind of one big bet that we have in robotics at Google, is that this large-scale machine learning could be a way to really help robotics. So we want to be able to de-risk some of those questions for the community, right? Like, if we can actually buy a lot of robots and provide a lot of demonstrations, how does it scale? How does it work?
I think one of the slides, or one of the figures in the appendix, actually has somewhat like the way that we built up these skills one by one. It's maybe, I don't know what page it's on, but it's a little higher than that. Yeah, this one sort of shows like how these were built up over time, and how more and more skills were added, more and more data was collected, each time seeing signs of life for the algorithms and performance and improving upon that.
And you can see that from time to time there's a new skill being added, so that kind of goes from 0 up. In the meantime, there's also the underlying code is changing, so it's kind of like improvements over time.
So it goes up and to the right, which is what we all love. And was there major downturns in this project, like times where things didn't seem to work out, or you didn't exactly know what the problem was, things like this? Could you get us a bit behind the scenes into when things go wrong? No problems.
There's quite a lot. I'm just trying to think which one to tell you. But there's quite a lot also from previous projects. But I think one thing that was quite surprising to me personally, and I think we are still kind of working on that, is that if you classify approaches into, let's say, imitation learning and reinforcement learning approaches, if you spend enough time and data on either of them, you can get them to work. So some of the results that you see here, most of them are from behavioral cloning, but we can achieve very comparable results with reinforcement learning, either by transferring policies from simulation and then continue collecting with that policy and kind of fine-tuning it to a high performance, or by just bootstrapping from real data and improving upon that. But what is quite surprising is that combining these two has been quite tricky. So kind of having a single algorithm that can digest all of that data, that can digest all of the demonstrations, as well as the autonomous data that was collected, data that we collect in simulation and so on, and have it have all the properties that we want, so it performs at least as good as behavioral cloning, but it can also improve autonomously and so on. This has been quite surprising and tricky.
I want to maybe have a bit of make a bit of an outlook right here, because it seems we have a pretty cool way to go from skills that are described by language, but you have to define them. Let's just scroll to one of them. You have to define them ahead of time, right? You have to define, pick up the Coke can, bring it to you, find the Coke can, and so on. You have to design these. Even though they're described by language, they're a pretty fixed set. Now, the first thing that maybe one can think about is how to extend that set, and not necessarily extend it just linearly, but I'm thinking of something when I say, please clean up the table. You might not know what's on the table. So we need this kind of a concept of almost like a variable or an unknown, so the plan could be go to the table and then kind of decide what to do next. So the language model could get even, or has to get, a feedback almost from either the value functions or from the picture itself, right? Is that anything that's on your radar? Sort of, what if I have to adjust my plan on the fly to the state that I'm going to encounter? How could this model be extended to handle that? Let's say all the actions are in your action space, right? But you just don't know at the beginning which ones you're going to take.
Yeah, I guess right now we kind of count on the value functions to sort of collapse whatever your plan is into the thing that is actually possible in the world. I think one of the most, I guess, straightforward ways to do it, though maybe not straightforward in practice, is to use things like visual transformers or structured scene representations that actually tell the language model what's possible, so that they can start reasoning over it earlier on. The other thing is to add in something like these success rates, success detectors that say, okay, you tried to do this and it wasn't possible. So maybe you tried to find an apple that wasn't possible. Perhaps the next thing to do is try to find an orange that may actually be in the scene. So there's some combination of value functions giving it feedback about the scene. But right now we don't have anything that has the language model really, really reasoning over the steps, because the value functions take care of that interaction. But one could fine tune it on some data that allows it to do that is probably the most straightforward way to do it. But whether that works is open question.
I guess the other thing is, and this would really also close the loop or close one of the loops, is if I imagine that I also had a model that could take any visual input and then kind of describe that, describe what's happening in the visual input. So I'm going to give it a video of something picking up the Coke can, and the thing would come up with a label for it, this video shows pick up a Coke can, right? Then I'd have almost limitless possibilities. I could just let a robot move at random, essentially, let the language model or let this model describe what it's doing, then kind of feed that to the language model and so on. So instead of you designing the actions that it should train, I could just let it do stuff and then have a model describe that stuff and then use that. Is that a plan, or is there a major hurdle on the way there? Because that will kind of result in a almost autonomously learning system if you give it a good language model. The language model could even also prompt it what to try next, right? The language model could be okay, what should I learn next? I should probably learn to pick up an orange. And then you just random around until the description model says, this looks like picking up an orange?
I guess I can say something first, and then I will ask like Karol, because he has previously Karol and Brian worked a little bit on like learning from play data. So what you described kind of similar to that. What I want to mention is that we find language is a great kind of state abstraction, because people invent language because they abstract some state, right? Like every word, every sentence is meaningful. So there's some work in language showing that like using language abstraction can improve exploration. For example, you can use that to guide your exploration and summarize current state. So that's one potential direction that we can go.
Yeah, I think there's kind of multiple ways you can see pushing this to an extreme. I think like one small step in the direction would be, rather than having these predefined skills, label everything in hindsight, as I think you're describing as well, and train policies based on the hindsight labels. So it's not just pick up an apple, but no matter kind of however the person that looked at that video described it, that's the skill that the robot was performing. And then you maybe don't have to constrain the language model to pick across the skills that you train, but maybe you can just take the generative output and see how that works. I think there is also a potential research to be done in how much can language actually take from the robotics problem and how much can it help solving it. So right now we are operating at a certain level of abstraction, like you command things like pick up the Coke can, and then the language model can operate on that. But you can also imagine operating on a much lower level, which is just like, move this direction or that direction or something like that. And the language model commands all of that. And you can choose where in that abstraction you want to be. And I think it's quite interesting that we at least can try things like this because of how good language models are today.
Yeah, and I guess to that, there's also works on using language basically to predict rewards, like over states. And so that's like one way to kind of like hook it all together. We have this like general framework.
What's the biggest hurdle? Like what's the biggest, let's say, unsolved problem to push these sort of everyday robots, not the company, but like the expression, the robots that help us doing our tasks? Where's the biggest roadblock in getting these to a point where they could actually be usable?
I think right now, given kind of how much time we spend on different parts of the system, it's the skills themselves. The bottleneck is still the robot actually doing the thing that you ask it to do. Even though these skills are simple, to get them to the place where they generalize to any environment, can kind of pick up any object, even the objects that it wasn't trained on, and do these tasks with large diversity of objects, environments, and so on, to very high performance. This is still really, really hard. So I think if we get much better skills, underlying skills, then we'll would have made a big step towards this actually being very useful.
I was going to say, along with those skills, like the way that we use the value functions is that as the skill improves, so does the like value functions estimate of what it can do. So it's kind of nice. We're like positioned both to use these skills, but it also improve the overall algorithm by having a better estimate of its success probability. So I think SayCan itself is at least set up in a good way to sort of like scale along with as this bottleneck is relieved.
Last question from my side. What do you think of the Tesla bot? And I'm going to give you the short pro in briefly in that it is the ultimate platform because the world is designed for humans, right? So if you have the humanoid robot, conceivably it could do anything the human can, at least mechanically. Does this sound good to you, or is there like major skepticism? No comment. You can wager bets right now. I
think one thing that is maybe that I'm excited to see is I think Tesla has the ability to scale things up quite well. They seem to be a really good hardware company, And so it would be interesting to see how some of the problems change. This is also things that we are researching as well, how problems change and how solutions change when you have many of these robots. So I would be excited to see if they have any good insights there.
Is there last things that we maybe haven't touched on yet that you would like people to know? Here, just for visuals, I'm showing some of the successful episodes at the end, which are quite impressive, like very multi. So there's just one robot. Just this is a collage, but very multi-step things, and I think that's just really impressive. Very long horizon planning things down to these individual actions. Yeah, that's pretty cool. Any last thing you want to let people know? How can they get started? Where can they find out more information?
Just want to mention that we have the website. On the website, we have a couple of videos demonstrating how the robot works and how the inference process works, along with the decision process, all the scores that we have calculated, along with the robot execution. So if there are anyone interested in how our algorithm works, definitely check that out.
I think I guess what I'm most excited about with it is how interpretable it is, that you can actually see how the decision is being reached by the robot, that you can see that the language model likes these things and that the affordance model understands that these tasks make sense or do not make sense in a given world embodied environment. I think it's nice that it scales really well to adding in new tasks as we go. And then I guess towards how people would use it, I think to start, the paper and the website's a good place to go. I think we're planning to open source a version of it on a more kind of toy environment in the coming months. So hopefully that'll be an exciting, easy way to sort of get in the mix with both this and language models. I think there's a lot of power in leveraging language models and kind of giving them these hands and eyes to execute real world tasks. I also think you had a point earlier about basically we use affordances, but really it's just a value function. And so this value function doesn't necessarily have to map to an affordance. And I think that's a really powerful idea, that we're basically taking all the knowledge in a language model and then hopefully applying it with a value function that isn't even necessarily normalized to, can you do this or not? It's sort of what's helpful, what's possible for whatever the RL train policy is doing. So I think that's a really, open space.
Yeah,
Cool.
I'm also quite excited about how language can kind of chip away a little bit from the robotics problem. I think that's something that we haven't really thought about that much before. And we see that we can handle much longer horizon commands, abstract commands, and so on, while keeping the policies fairly simple. So I think it's quite exciting to see how much further we can push that direction.
Yeah, I think representations have always been such a challenge for, especially task representations are such a challenge for robotics. And I think language has provided this really nice interface to interact with the robot and then have the robot interact with the world.
Excellent. Well, Karol, Brian, Fei, thank you very much for being here. This was a lot of fun, and I hope to see you again soon.
Yeah, thank you.
Thank you for having us.